not the little itty bitty ones. So we're all going to be taking the exam there. It's big enough for us to space out, to separate out. So that way we don't have to, we do not have to mess with this. So don't forget that on Thursday. Go find that room. Okay, if you haven't been in the community core before, I'm going to rely on the TA to show me where it is, basically. I sent her, I was going to say, I sent her to find it because I didn't have time to go look it up. But allow yourself a few more minutes to try to find that classroom. For some reason, the community core is a maze. That's what I've heard. But our TA managed to find it, so.
Good transport there is like, I think that's community core. Like the first day, I don't think anyone found the classroom.
Yeah.
Is it that one?
So I haven't seen it yet. I can't describe the way to it, but hopefully, if nothing else, if you show up 10, 15 minutes early, you can walk with us. I'm going to ask the TA to come in around 12:30, 12:35, and I'll walk over there. So there will be no one here, in other words, on Thursday. Okay? So let's look at, so this is the one that I had uploaded. I don't know if you have tried it yet, but there were no solutions on up on Sakai for this. And the reason was I wanted to walk through it with you, right? So we have a toluene storage tank, 2 meters in diameter and 5 meters tall. It's being refilled from a tank truck through the piping system shown in figure 1. So the first thing to notice here is that there is absolutely no information from this section. It says from tank truck. You have no idea how far away the tank truck is, what the pressure is, what they're pumping it with, right? In other words, that's irrelevant to the problem. Okay, then we have a storage. The storage tank is vented directly into a local exhaust. Okay, it's an elephant truck, and that is done to prevent flammable atmosphere. But key here is that assures that the storage tank remains at atmospheric pressure during the filling. Okay, and because otherwise, if we're pumping liquid into a tank and you're not actually letting the gas, replacing the gas, you might actually pressurize the tank a little bit. Okay, so all that wording was just to make sure that you can say that in this tank we have a PG gauge pressure of 0. Okay, then we have commercial steel piping, 5 centimeters in diameter, but it's rather old, and one day during the filling process, a 1 centimeter hole forms here due to rust. Okay, and the filling rate of toluene from the tank truck is 3,000 liters per hour. And you are asked to find the pressure in the pipe at the location of the hole. Okay, so I made it easier for everyone last year because I could have said, what is the mass flow out of this hole? By asking you to calculate the pressure first, I'm telling you how to do the problem. Because if you calculate the pressure, B is actually to calculate the mass flow rate. But in A, you now calculated the pressure that you need. And this is the situation where it turns from flow of liquid through a hole in a tank or through a pipe to flow of liquid through a hole. Because we know the pressure at that location. That's all we need. And it simplifies that calculation significantly. Okay. Also, knowing the flow rate through here and therefore the linear velocity through the pipe simplifies things, as we know when we have set it up previously. Right? Some of the things we can't directly solve for, so we have to either do it iteratively or use a computer, right, or a calculator to graph it, or however you want to do it. know you've seen this problem and we talked about it. And I don't know if did anyone attempt this one? So that you know what the answer is? No, not yet. It's too early. The exam is not until Thursday, 2 days away. Okay, so the key here is to realize that you do need to, your system, and here is where this was extremely difficult for me to grade. Because, and the reason is, if you don't tell me what your system is, I have to guess, right? So if you clearly state, here is my system, then I know what you're doing. So the key is you need the pressure here. You define your system as this tubing. What is over here is totally irrelevant, not needed. This thing here is just a realistic piping system. You use this to fill this tank or this tank. So there's a tank on this end too. But it's closed, so this part, this valve has nothing to do with your system. Question?
I want to say in fluids we might use that as like a source of the total.
So
What
this
is it,
will do
friction or-
something, you mean the T?
The closed value
valve.
valve and the open value like would affect the flow rate or
Right.
something.
Right, so what we are going to assume is that whatever affects the flow rate is the T.
Okay.
And the T in this case is used as a run through, not an elbow. So that's where this part here will affect the flow rate, but we're using it as a run through. There's no flow here, so it's closed, so there's no flow. Right, so whatever goes in here, right, let's just say before the hole opens up. Even after, whatever enters this pipe comes out the other end. Okay, so, but before there's a hole, whatever we are pumping through here is coming out this way. It's an incompressible fluid, so the velocity here, the linear velocity through the pipe would be the same here as over here, incompressible. Okay, how tall the tank is also totally irrelevant. We don't need that. We know when we're gonna splash fill this because it's gonna come out, but that's not what we're dealing with in the problem. We need to calculate the pressure here. We know what the pressure here is. It's atmospheric. Okay, any questions on that? Okay, so if we go back to the actual problem, right, we define our system, and the key things was tank remains at atmospheric pressure, gauge is 0. We have commercial steel piping, we have the inner diameter of that pipe. The hole is 1 centimeter due to rust. Okay, and here is the, the assumption that is roughly, you're right, that's the diameter is probably, you're not gonna open up a perfectly square hole through rust. It's more likely, it's not gonna be perfectly circular either, but that's a better approximation than square, I would say. If you had said, I'm just gonna assume that it's a square hole, I probably would have given you full credit because it doesn't say 1 centimeter in diameter. But most likely it's, right, that's the diameter of a circular hole. It's due to rust, okay, so that's information that we need. Commercial steel due to rust, and then that will give us the volumetric flow rate. Here will give us the linear velocity through the pipe. Okay. We're faced to calculate the pressure. We'll go in here, we needed, if you look here, we need 2 fittings. We need this T and this gate valve, and then we have 9 meters or tubing total. Okay, the hole is after the elbow, so these 2 elbows and these 3 meters have nothing to do with the problem. Okay, I did have a few students who calculated the pressure up here first. Okay, did the system like this, calculate the pressure up here first, and then did the pressure over here. That's perfectly fine, it's just a lot more work, right? Let's do the easier way, right? You don't have to, that was sort of overkill. You don't need that. You just make sure that you define your system so you get the right answer. Okay. So we go into the fittings table. We have T's. You see there are 2 ones used as an elbow. So if the tank had been on the other side, where the closed valve was, we would have had to use these, right? T used as an elbow because it did the 90 degree. In this case, it was run through, and you know what, I didn't copy over. The actual figure caption was stating that all fittings and joints were welded or flanged. Okay? If it didn't say anything, that's what I would assume. It's not common that you have threaded pipes like this, unless perhaps it's PVC. Okay, so this means here these are flanged, which means these would be welded. Okay, so that's why we go in. We use a T as a run through, flange, welded. This is our K1 and our K infinity. We had a valve, and I do believe I specified that it's a full line gate valve, full line size gate valve, so that you would know that you would need those two. The other information we were given was that it was commercial steel. Now the hole was due to rust. So this time I specified what I wanted you to use, which is the general rust values. So in other words, your epsilon here, the roughness factor, should be 2 millimeters. Okay? The new would be worst case scenario, but that's not what we have, right? The conditions are stating that it's a rusted pipe. Okay, part of the reason why I did that was so that we're close to fully turbulent flow. Okay, so if you look at it, the Reynolds number for these conditions after we calculated, I'll give you all the numbers for this and for you, but it's about 36,000. Okay, so 10 to the 4, we're about here. Okay, but that rust gives us a relative roughness of 0.04, so we're up here. In other words, what did I say, 10 to the 4, 3, so we're right at the cusp, okay? I was trying really hard, actually, to get that to be in the fully turbulent region, so that you would know that you could use that as an interval. It's close, and I'll give you the numbers to see what, how much it differs. But in other words, since you have the Reynolds number and you have the roughness factor, you could read the feigning friction factor from this graph. That would be perfectly fine. Okay? Or you could use either one of the equations, right, for the feigning friction factor. It's easier in this case because we are given U, so we know what the Reynolds number is. Okay. In B, you're asked to calculate the mass flow rate of liquid through that hole, and I am giving you, if you did not get the pressure in from A, I'll give you pressure to use in B. Okay? And in any time, even if you had a pressure in A, and just to make sure that you feel like it's not quite right, you're always allowed to use that. Okay? I wouldn't, now if you had the wrong value, you would not, you had points taken off for that in A, so I wouldn't take off points for that in B. It's just easier for me. If you use this value, then I know what the numbers are supposed to be, right? So I had a few students who were not certain, and they just used this value. Now, what is that though? Is it gauge or absolute pressure?
Absolutely.
So, exactly, it's absolute pressure, because it doesn't, I would state gauge pressure. The pressure at the location is such and such gauge. So it's about 4 kilopascals, right, gauge. Okay, any questions? Seem like an easy problem? Maybe? Perhaps? Okay. Let's see, let's go walk through it, maybe a little quickly, if you're okay with it, to just make sure we're on the same page. You know where all the numbers are coming from now, right? So think I'll take off this, right, you saw all the numbers, so we can, so this is problem one. Same one. 2015. Okay, so I'm just gonna draw this pipeline, right, we have our T here. And the gate valve, and then, so this is our second point, and our hole is here. This is gonna be our first. And we were given, I'm not entirely sure what to, right, in terms of what to use for volumetric flow rate, so volumetric flow, hold on. It was given at 3,000 liters per minute, and that gives us,
Was it per hour?
Yeah, he was right.
was it per hour?
Yeah.
Yes, it was per hour. Yeah, that's, per minute, that's pretty high. Okay, so it is 3,000, that's cubic decimeters, so that's 10 to the negative 3 cubic meters per hour. We had a pipe diameter of 5 centimeters, right? So 2, this would be cubic meters times pi. And that is equal to 1,528 meters per hour, and it is about 0.4244 meters per second. Okay, that gives us a Reynolds number, so the problem, which I didn't show you here. If you look at the exam one, the density and the viscosity for this problem is given at the end of the exam. Okay, I'm gonna be a little bit better and put it where it actually belongs. But both problems had to do with toluene. Okay, so we had all the information we needed. That's the actually not the needed. So it's diameter, velocity times the density over the viscosity. Again, make a note of this equation in your book, unless you can't remember it. Meters times 0.4244 meters per second. The density was 866 kilograms per cubic meters. And I believe I gave you the viscosity in 0.005 kilograms per meters in second. Okay, that viscosity is sometimes given in millipascal seconds. Okay, which means I expect you to be able to convert that. Okay, so what do we have? That's 10 to the 3 Pascal, that's Newton per square meters. And second, Newton is what?
Kilogram meter per second squared.
Kilogram meter per second squared times second. And then, what did I say, over square meters. So it's the same units, right? But if you look up viscosity, that's probably what you will find, right? Unless you're looking at kinematic viscosity, that's, right, we want this one.
What did it say? I can't, was like.
So so for U, which is the viscosity, millipascal
No,
seconds.
what's the number?
The number here,
No, the one before it, that I can't, that one.
this is mu, the symbol for viscosity.
Oh, okay.
Sorry.
So mu is given in millipascal.
Yeah, so if you look up this on the web or something, right, it's often given in millipascal millipascal seconds. Okay, but Pascal seconds is